This video is on standing waves. You do need to watch animations on standing waves to perfectly understand it, because things are moving in standing waves. Please do go to this website and check out the animation. Please do treat standing waves and traveling waves differently. Question 1. List some observations which can be made from standing waves but not traveling waves. So when we learned about diffraction and refraction, those were all traveling waves. Now we're going to learn about standing waves. A standing wave is made of two traveling waves traveling in opposite directions. Okay. Sometimes we don't draw both waves, just the displacement, the resultant displacement. Energy is transferred, but the particles' energy is not transferred, but the particles do move between the nodes. Recall that traveling waves are good at transferring energy, but not matter. So I'm telling you that standing waves do not transfer energy. All vibrations are simple harmonic motion and have the same frequency. Between two nodes, the maximum amplitude is different for all particles or points in the medium. All particles or points between the two nodes are in phase. All the particles or points between the two nodes move in the same direction. The particles or points in the adjacent or next node are out of phase. Nodes look like the location of a compression or refraction. Antinodes are the location of particles moving with maximum displacement and speed. And the ends of a standing wave are always nodes for closed ends or antinodes for open ends, nothing in between. So take a look at this image. This is what we call a closed pipe, because both ends of the pipe are closed. So we're going to have two waves traveling in opposite directions, and they're going to interfere with each other. Where you see zero displacement, we call those nodes. So there's four nodes. Where you see maximum displacement, we call those antinodes. So there are three antinodes. So suppose this 1/2 wavelength on the very left side, all the particles move to the right. At that same moment, and the half wavelength in the middle, all the particles move to the left. And then the half wavelength on the very right, all the particles move to the right. And in the very next moment, all the particles in these half wavelengths are going to move in the opposite direction. So if you want to take a look at this half wavelength on the very left, in one moment, all the particles move to the right. Then the next moment, they all move to the left. Then the next moment, they all move to the right. Then the next moment, they all move to the left. They don't move up and down, the particles. Where we have this maximum amplitude, this antinode, that's where we get the maximum speed of the particles. Where we have this minimum amplitude, like zero displacement, near the nodes, we get zero speed, or very low speed. And the frequency of all of these particles moving to the right and the left is the same. Question 2, define the following terms. Node. Node is a location on a standing wave which has zero displacement. This is a location of maximum compression and maximum refraction. So how many nodes do we have in this figure? We have 4 nodes. Antinode, that's the location on a standing wave which has maximum displacement. So let's look at this image. How many antinodes do we have? We have 3. Part C, first harmonic. That's the standing wave with the longest wavelength and the lowest frequency. So the first harmonic, it's when we have this closed pipe or tube, and we're only going to get half a wavelength. Right now we have 1.5 wavelengths. And fundamental frequency is the frequency of the first harmonic. Part C. Below are the first 3 harmonics of a tube with both ends open. The frequency of the first three harmonics are derived for you. Draw and solve for the next three frequencies on the next page. So this is what we call the first harmonic of an open tube. Both ends open. So remember, if it's an open tube, we have an antinode next to the open tube. So the length of this tube is lambda over 2, meaning we only see half a wavelength. Now let's solve for lambda equals 2L. Let's introduce the equation V equals lambda F. Now let's substitute lambda equals 2L in that equation V equals lambda F. So V equals 2LF, and let's solve for F. So this is the fundamental frequency for an open tube. F equals V over 2L. Now for the second harmonic, once again, we have an open tube. L is equal to, the length of this tube is equal to how many wavelengths? It's one wavelength. So L equals lambda. Let's introduce the equation V equals lambda F. Let's substitute lambda equals L, so V equals LF, and solve for F. Let's take a look at this third harmonic. L, which is the length of the tube, is equal to how many wavelengths? Let's count it. It's one wavelength, 0.5, so it's 1.5 wavelengths. Let's solve for lambda, it's 2L over 3. V equals lambda F, and lambda equals 2L over 3, so substitute that into this equation for lambda and solve for F. So this is the frequency of the third harmonic. So we could see what we did for the frequency of the fourth harmonic, the fifth harmonic, and finally the sixth harmonic. Now remember, these are open tubes. Now, question 4. Below are the first three harmonics of a tube with one end open and one end closed. Okay, so let's solve for the frequencies. So when one end is open, we have an antinode. When one end is closed, we have a node. So how many wavelengths do we see here in the first harmonics? It's L is equal to lambda over 4. The length of this tube is equal to lambda over 4. So solve for lambda equals 4L. V equals lambda F. Substitute for lambda. Finally, solve for lambda. So solve for F. Okay. So this is what we call the first harmonic, the fundamental frequency, V over 4L. Now, if we have an open closed tube, there's no even harmonics. It's just first, third, fifth, 7, 9, 11. You could see here, the length of this tube, L, is equal to 3 lambda over 4. So now, once again, solve for lambda. We have V equals lambda F. Substitute lambda into this equation. Let's finally solve for F. Here we have a fifth harmonic. L, the length of this tube, is equal to how many wavelengths? 5 lambda over 4. The second line, we're solving for lambda. The third line, we're introducing the equation V equals lambda F. The fourth line, we're substituting for lambda. Finally, the fifth line, we are solving for F, frequency. For the seventh harmonic, how many wavelengths do we have? We have 1.75 wavelengths. Once again, solve for lambda is step 2. Introduce the equation V equals lambda F is step 3. Substitute for lambda is step 4. Finally, solve for the frequency. This is the frequency of the seventh harmonic. You could see what was done with the ninth harmonic and the 11th harmonic. Question 5. Below are the first three harmonics of a tube with both ends closed. The frequencies of the first three harmonics are derived for you. Draw and solve for the next three frequencies on the next page. So remember, if it's a closed end, we're going to have a node. So it looks like this for the first harmonic. So L, the length of this tube, has 1/2 wavelength. Then solve for lambda. Introduce the equation V equals lambda F. Substitute for lambda. Finally solve for F. So this is the first harmonic, the fundamental frequency. See what I did here for the second harmonic and third harmonic. See what was done here with the fourth harmonic and fifth harmonic. Finally, see what was done here on the sixth harmonic. Question 6. Give an example of a standing wave formed in an open pipe. That's air flowing in both directions through a horizontal or vertical pipe. Question 7. Give an example of a standing wave formed in an open-closed pipe. So here's an example. A vertical pipe with the top end open and the bottom end in water. The amount of water can be decreased to change the length of the open-closed pipe. So we could also raise or lower the pipe. A tuning fork is placed on top of the vertical pipe. A sound wave is created from the tuning fork will bounce off the water surface and create a standing wave. So this is open-closed. Another example is a horizontal rope connected to a vertical wall. One end of the rope is open and vibrates up and down. The energy travels horizontally and is reflected from the wall. So here we have two waves, yeah? The direction of the vibration creates one wave, and then the wave bouncing back from the wall creates the other wave. Question 8. Give an example of a standing wave formed in a closed pipe. That's like a plucked guitar string. Question 9. A string is stretched between two rigid supports which are 1.20 meters apart. The string is plucked and it is noted that a standing wave is formed on the string which consists of 5 nodes, including the endpoints, and 4 antinodes. So I drew the image here. We got 5 nodes where the displacement is 0 and 4 antinodes. So here's a note. If there is dirt on the ground, then it will collect at the locations of the nodes. So imagine we put some dirt on the ground. Where we have the antinodes, the dirt's going to be pushed left and right. So we end up getting dirt just where the nodes are on the bottom. So what is the wavelength of the standing wave? Well, the length is 1.2 meters. And how many wavelengths do we have? We have 2 wavelengths. So solve for lambda. Part B, if the frequency of this vibration is 220 hertz, then what is the frequency of the fundamental frequency which will vibrate in the string? So use the equation V equals lambda F. Lambda 1 F1 is equal to this. And lambda 4 F4 is equal to this, which we knew previously. From this part. So set V1 equal to V4 and solve for F1. Part C, what will be the frequency of the 5th harmonic which will vibrate in this string? So let's draw it out. The 5th harmonic is going to have 6 nodes. So we could solve for lambda. And then we have these 2 equations. Now the speed is going to be the same. of the wave traveling through that string. So we could set V1 equal to V2. Question 10. Transverse waves are being generated in a string between two fixed points, which are 3.5 meters apart by a wave oscillator which is generating a frequency of 28 Hertz. Part A, what is the wavelength of the wave? So the wavelength is 3.5 meters. Sorry, the length of this is 3.5 meters because it was given to us. And how many wavelengths do we have? We could count it, it's 3.5 wavelengths. So lambda is equal to 1 meter. What is the speed of the wave? V equals lambda f. We know lambda, we know f, because it was given to us. Part C, what is the lowest frequency which could be used to generate a standing wave on the string? The lowest frequency, we could see this is half a wavelength, 0.5 lambda. So for the fundamental frequency, the wavelength is 7 meters. V equals lambda f, solve for f. Part D, what is the wavelength of the lowest frequency wave which could form a standing wave in the string? We already figured this out from part C. Part E, what other frequencies could form standing waves in the string? So the fundamental frequency is 4 Hertz, that's half a wavelength. The next one is going to be this image here, which is 1 wavelength, which is 8 Hertz. So we get 4 Hertz, then 8 Hertz. So we conclude that F is going to be equal to 4 Hertz times N, where N is a positive integer. Question 11. Consider the string vibrating below and forming a standing wave with a frequency of 180 Hertz. The length of the string is 1.50 meters. So part A, what is the wavelength of the wave? So the length is 1.5 and there's 3 wavelengths. So just solve for lambda. Part B, what is the speed of this wave? V equals lambda f. Lambda is from part A, f is given to us. Part C, what is the fundamental frequency which will resonate in the string? So L, the length of the string is 1.5 meters. How many wavelengths do we have here in this image? It's 0.5 wavelengths. So solve for lambda. V equals lambda f. So V was solved from part B. Part D, what will be the frequency of the third harmonic which will resonate in the string? So the third harmonic means 4 nodes. So L is equal to 1.5 meters, which is 1.5 wavelengths. We could see from the figure there's 1.5 wavelengths. So lambda is 1 meter. V equals lambda f. So just solve for f. Part E, what will be the frequency of the ninth harmonic, which will resonate in the string? So ninth harmonic means 10 nodes. So L equals 1.5 meters, which is 4.5 wavelengths. We could just count it up. So lambda is 1/3 of a meter. V equals lambda f, solve for f. Question 12, a closed guitar string has a standing wave on it. The distance between the 4th node and 9th node is 50 meters. What is the wavelength of the standing wave? So let's draw it out. That's what I did. I just drew it out. Okay. So I drew a wave and I said, okay, let me label the 4th node and the 9th node. What is the wavelength of the standing wave? Okay. So that's what you do. Question 13. An open pipe has a length L. State an equation for the frequency of vibration of the first harmonic, fundamental frequency, standing wave, which can be set up in the pipe if the speed of sound is v. So we've done this before. Step 1, solve for lambda. Step 2, use the equation v equals lambda f. Question 14. An open closed pipe has a fundamental frequency f. What will be the first harmonic fundamental frequency of another pipe of the same length which is open at both ends? So take a look at the left-hand side. Step 1, L equals lambda over 4th and solve for lambda. Step 2, use the equation v equals lambda f. Now look at the image on the right side. Now this is open at both ends. Step 1, find a lambda. Step 2, find f prime. F prime is not the derivative of f. So now compare the two. We know f prime is equal to 2f. Question 15. Pipe A has a length of 2 meters and is open at both ends. Pipe A produces a frequency of 36 Hz when the air inside it vibrates in its first harmonic. Pipe B is closed at one end and also produces a frequency of 36 Hz when the air inside it vibrates in its first harmonic. Calculate the length of pipe B. So just draw an image or images. So the first one is open at both ends. The second one is closed at both ends. So we could see step 1, we solve for lambda. Step 2, we use the equation v equals lambda f. And now look at the image on the top right. Step 1, we solve for lambda. Step 2, we use the equation v equals lambda f. Step 3, we're going to set the speeds equal to each other, because the speed of sound is going to be the same in both of them. So L is equal to 1 meter. Question 16. Water is in a vertical cylinder. A smaller vertical cylinder is inside the larger vertical cylinder. A tuning fork which produces a vibration with frequency F is placed above the smaller cylinder. When the length of the smaller cylinder above the water is L1, a maximum sound is heard at the first harmonic, fundamental frequency. Water is then drained from the larger vertical cylinder. When the length of the smaller cylinder above the water is L2, another maximum sound is heard at the third harmonic. Determine an expression for the speed of sound in the smaller cylinder in terms of F, L1, and L2. So, step 1, let's find the wavelength from the image on the left. That's when we have half a wavelength. Step 2, let's find the wavelength when we have 3/4 lambda. Step 3, let's just subtract the two. Let's subtract these two equations. And then we end up getting V equals lambda F, which is this 2 L2 minus L1 times F. Question 17, consider two pipes. Pipe A is an open pipe with a length L. Pipe B is an open closed pipe with the length L prime. Remember, that's not the derivative. The frequency of the first harmonic of both pipes is the same. Calculate L prime over L. So they're talking about the frequency of the first harmonic. So let's just draw the first harmonic of an open open and open closed. So once we divide the two, we get 1/2. Question 18, consider two pipes. Pipe A is an open open pipe with the length L with the first harmonic of 300 Hertz. Pipe B is an open closed pipe with the length L. Calculate the frequency of the first harmonic of pipe B. So you could see what I did here. Step 1, I just looked at the open open pipe. Step 2, I looked at the open closed pipe. Now I got two equations here, yeah? Step 3, the speed of sound is going to be the same for both. So just set V equal to V.